I heard it picked up 5 hours over.
Yeah, gone. I was actually gonna leave. I woke up and I was like, well, I could just like go after like all the patients today. Just work on it at a chill pace instead of like frantically trying to get everything done by then. Yeah, grading. Good. Pretty much now that you have Yeah, I did it really fast, and also since it was the second test, there were 0 of them had issues. They all actually, so I did it all. And then I ended up every TA was multiple until other than office, but so I was just saying, English, you want to work with it.
There's like a little layer.
Yeah. I'm gonna try and get this by tomorrow, and then so I can do Saturday and Sunday. But if it's so if they'll help stuff. I'm still like I find it making it. So it's a 7. I don't think third. Okay. You're right, though. Yeah, that seems to be the thing. So I'm trying to just take stuff that's
Is he just trying to register something more? That's just usually the way I do
Alright, so today we're going to continue the discussion on the last part of this course, which is crash recovery. And I'm planning to spend about 20-25 minutes to wrap up this discussion. Then the remainder part of this lecture, I will be using that for 2 items. One is to give you a quick review of the final test coming up next Tuesday. Then use another about 20 minutes also to 20 to 30 minutes also to quickly branch out to some other topics on large-scale data management systems, including Spark, MapReduce, and a few NoSQL systems. I'll quickly just give you an overview what they are and what are the differences to the relational database system where we've been talking about for the whole semester. So, that being said, let's rewind to where we stopped on Tuesday. So we talked about Red Hat login. To quickly remind you, Red Hat login basically enforces 2 policies. One is you must force a log record for update before the corresponding data pages get to the disk. This is to ensure that your system is able to perform undo, right? So basically the idea is if you are able to force the log record to disk, then you can use the no force policy. No force policy says a dirty page can be written back to disk over a committed data. A dirty page caused by an uncommitted transaction can be written back to disk before the transaction has actually committed. But if you want to allow that to happen, you need to be prepared to be able to do undo in the case if that transaction later is aborted for whatever reason. That's what we call no force policy. If you're using no force policy for the actual updates on data pages, then you must be using force policy for the log records, which is to say the corresponding log record must be written back to disk before the buffer manager can write an uncommitted write back to disk over a committed data. This is to ensure you can undo. That's policy number one. Policy number two. That's for the no steal policy. The steal policy says uncommitted data pages in the buffer manager can be written back over a committed data. Okay, that's to support the steal policy. Policy number two, you must force all log records for a transaction before commit. This is to ensure you can redo. In the case that a transaction has committed, but not all the changes made by that transaction have made back to disk. Right? Because we're using what? We're using no force. A transaction can commit without pushing all the changes made by that transaction back to disk. This is called no force. If you are using no force for all the dirty pages caused dirty by the current transaction, meaning you allow the transaction to go ahead and commit without pushing those pages back to disk, you must make sure the corresponding log records are forced to disk before the transaction can actually commit in order to support redo in the case of system failure. Right? A transaction has committed using no force, so not all the changes made by the transaction have been made back to disk. Later on, system has crashed. Some of the changes made by the transaction, committed transaction, are still in the buffer and are not reflected on disk yet. If system crash and you don't have all the log record on disk yet, then you are in trouble. There's no way you can redo the changes made by that transaction. In other words, you will fail to enforce the durability requirement. Question?
What about with number one? It seems like that could cause issues if, okay, you update log, or I guess you force the log record to update because you're going to write it to disk.
Before the database
crashes.
Before the corresponding database can be written back to disk. Yeah. And
so I was wondering, I guess.
That's to ensure undo. That's to ensure autonomous. Okay. If system crash, the point is if system later crash and that transaction has not been able to commit yet, the fact that you have all the corresponding log records before the dirty reads are written back to disk, meaning that implies you can redo the changes made by those dirty reads.
Okay, so you don't get rid of the log record until they committed.
You don't get rid. What do you mean by get rid of? What do you mean by get rid of log record?
Because I'm just saying with number one, the situation is probably going to happen where maybe they've already committed, so the log record is there.
Maybe a transaction has committed. Okay.
Yeah, so you're going to now persist that log into the database.
Well, so by requirement number two, a transaction cannot commit unless all log records are written back to disk. So by that time, if a transaction has committed, all log records for that transaction must have been written to disk already.
Okay.
So these two work together.
Do you not delete the log record from disk until you've updated the database?
Well, what you're talking about is, for now you can assume log file is kept forever.
Oh, okay.
You don't truncate the log record. Of course, in real database system, you do truncate the log file to save space and for other purposes. But for now, we assume log file just is kept on permanent storage forever. Okay?
Alright. So I guess you don't move you don't say that log record is processed until you've written that data page to disk or something.
No, I don't get what you're saying. What do you mean you don't? Okay. No, just imagine all the log records written back to disk are permanently stored there forever for now. I will talk about when we actually truncate the log file.
Oh, okay.
Okay. So these two work together. And this this ensures you can do both redo and undo. Now, let's formalize mathematically what exactly we're talking about here. So essentially, we have a bunch of players. We have the log, we have the data page, we have log file, this kind of so on and so forth, right? So on each data page, we introduce something called page LSN. Page LSN stands for the most recent log sequence number, for the corresponding log record that calls the last write to that page. So this page may have received multiple writes in the past. I am interested in documenting the log sequence number of the last write to the page. Is that clear? That's what page LSN is. So if you understand this, and also system keeps track of flush LSN, which is the maximum value of the log sequence number that's been flushed to disk so far. So basically, I have a bunch of log records in memory, in buffer. So these are my, suppose these are up to here is my, so last or most recent log record. This is memory. And this is my disk. And push some of those log records to disk, right? So because we are not using, notice that we are not forcing any log record to be written to disk immediately after the creation of the log record in memory. We're not doing that. So there must be some inconsistency from here to the set of log record on disk. This must be a subset of what you have here. For example, up to here. Does that make sense? And these are the few log records you haven't written back to disk yet. And this is what we call flush. It's a single value. You don't have to remember the actual log record, just need to remember the log sequence number corresponds to that particular log record. Is that clear? So that's what it is. That's what this says. So this part is the red color region on disk. This part is that black region, the tail part in memory that haven't been written back to disk yet. Page LSN, if you recall what I just said just now, is the most recent log record, the log sequence number for that log record that caused the page to be dirty, which means this page was brought into memory by some transaction. Since then, one or more writes might have happened on this page, either by that transaction or by a combination of multiple transactions. Okay, one transaction can do multiple writes to the page, or each transaction might have done a few writes. I don't really care. I only care the log sequence number for the last write to this page. That's essentially what page LSN is. Is that clear? It doesn't really matter which transaction it comes from. I only document who made the last write to my page. That's page LSN. If you understand this, Red Hat logging, the first requirement for Red Hat logging says what? Must force the log record to the disk before the corresponding update were written back to disk. Translate to our representation now, that essentially says this. For any page, page LSN must be less than or equal to flush LSN. Before you can write this page to disk. So only these pages, in other words, only these pages are candidates for buffer replacement. Remember, in the past, our buffer replacement policy says you can replace a page if and only if the pin count is 0. Now we have an additional requirement. You need to have pin count equal to 0 and page Alison less than or equal to flush Alison. Does that make sense? This ensures that what? This ensures what? Redo or undo? Someone explain. This ensures redo or undo. Huh? This ensures redo. Basically, the corresponding log record has been flushed to disk. The page has not been flushed to disk. System crash, you lose the page forever. However, you do have the log record. You can actually this help you to do both redo and undo depending on the situation, right? So you have the corresponding log record on disk already. So it's okay to lose the page. You can either reapply the update or de-apply the update because the corresponding log record is already written back to disk.
Why is it less or equal and not just less?
Oh, equal is fine. Equal means that the last record flushed to disk is exactly the log record causing this page to be dirty. Meaning that the log record is already permanently stored on disk, so I can actually write this page back to disk now. But you cannot take a page whose page Alison is greater than flush Alison and write that page back to disk. Why is that? If you do that, what happens? If you do that, you will not be able to undo, potentially you are not able to undo the change made by that page. Why? This page has some uncommitted write. It's written back to disk before the corresponding log record is written back to disk. Now, system crash. Because you have written this page back to disk, that must be a result of buffer replacement. So this page is gone in buffer, is replaced. And system crash, the corresponding log record will be lost forever. The disk version, the committed version of this page has been overwritten. What you left on disk is the new version, the uncommitted version of this page. System crash, at this point you need to abort the transaction to ensure autonomously you are not able to. The committed value is gone forever. You have lost the log record. Okay? Is that clear? I hope that's clear. Okay? So essentially, that's the requirement for Red Hat logging. That's for the requirement number 1. Requirement number 2 says what? All log record for a transaction before it's ready to commit must be written back to disk. What does that mean? What that means is last Alison for a transaction must be less equal than what? In order to allow this transaction to commit. Okay, this is really to support that no force as I explained, right? So basically a transaction now can commit even if there are some uncommit, all the dirty pages caused dirty by this transaction are still in buffer. Even if your system has crashed, at this point, all my changes are documented by those corresponding log records, and those log records are permanently stored on disk already. So I can safely commit without worrying about forcing all the dirty pages to disk. Okay, so that's the second requirement for Red Hat logging. Okay, those are the 2 requirements. Now, take a closer look at the log record. We explained this last lecture, but now let's zoom in a little bit. We have log sequence number. We also have something called previous LSN, which kind of essentially they serve the purpose of linking log record from the same transaction. So the previous LSN documents the preceding log sequence number for the log record from the same transaction. The point is you are dumping log record from different transactions to the same log file. And you want to be able to quickly traverse through all log record of the same transaction for redo and undo purposes. Otherwise, you have to linear scan the entire log file to do this, to check whether it's having the same transaction ID or not, which is expensive. So we kind of build this implicit linked list for each transaction within the log file, using this previous Alison trick. Okay, so that's the idea of this field. Transaction ID, we explain type. You have a couple of different types of log records. The most common type of log record is update. If it is an update log record, we will have these additional fields, such as page ID, the length, the offset, before image, and after image, which I explained last lecture, so I'm not going to repeat myself. However, you can also have commit log record and abort log record. Commit log record is to indicate that the corresponding transaction starts committing. This is another critical thing to keep in mind. Commit process is not atomic. Transaction commit is not atomic. In the process of committing, system may fail, and a transaction may fail to commit. Why is that? What actually happened during commit? Well, when a transaction declares, I'm ready to commit, what the system will do is to start doing this, to ensure this. When a transaction declares, oh, I'm going to commit, it is very possible that the last log record from that transaction has not been flushed to disk yet. When a transaction declares, I'm going to commit, what the system will do is to start forcing those log records to be flushed. And once I've finished flushing all the log records from this transaction to disk, meaning this becomes true, the last log record from this transaction now is less than or equal to the flush Alison, that indicates the end of the commit process. So commit is not atomic. This takes time. System may fail in the middle of that. Does that make sense? That's why we also have an AND log record. The type can be AND, meaning that between commit and AND, things may happen. Similarly, a transaction may also declare abort. This is not a forced abort by system failure. Rather, a transaction decides to abort by him or herself. Abort, of course, is not atomic, because once you declare abort, what do? System has to go and send to this condition. Once you declare abort, system is able to undo all the changes because of this condition. But it takes time to load those log records from this back in memory and grab the before image for each update and restore the before image for each update. It takes time. That's why for abort is also not atomic. You will declare abort, and some point later you will declare AND. That indicates the completion of the abort process for that transaction. Finally, there are two special log record types. One is called checkpoint. This actually ties with Dillion's question earlier about truncating the log. I will explain this in a minute. And compensatory log record. CLR is another special type of log which is kind of hard to understand. For now, just remember there's this type. And it facilitates undo actions. It facilitates undo actions. So let me explain a little bit what checkpoint does. So all of you have gone through security check in an airport, have you? Okay. So if you have done that, what you notice is there are multiple levels of security checks at an airport. First is at the airline agency counter. They need to look up your record, make sure you have a boarding pass. So they print out the boarding pass. You have to at least do that. Then what do? You go to a long queue and show somebody your boarding pass in order to enter the queue. Then you wait until the queue is up to you, then you show the boarding pass and then you ID to a TSA agent. Only after that you can what? You can then proceed to the actual security check, which is take out your shoes, put your bag and all that. You go through this whatever, right? And after that you're not done yet. Finally at the gate, they will do another check of the boarding pass. Does that make sense? That's the typical process. If you look at it, it's multiple levels of security check, one after another. I don't know whether you guys have wondered about this. I have wondered about this. Why not? Why not? We aggregate all of this into a single point where I get my boarding pass, check my ID, take out my shoes, take out my computer, go through the scan, then I'm ready to board. No more check. One check for everything. That's an alternative approach. Does that make sense? It's definitely easier for the customer. If I have a choice, I will choose obviously the second option than the status quo. I don't know about you. I will choose the second option. Actually, the airport in Singapore, Changi Airport, does something like that. They actually build, believe it or not, I was amazed. They build a security scan, the big machine thing, at every single gate. There is no central security scan when you enter Changi Airport. You do security scan only right before you do boarding. At each gate. When you have money, you can afford to do that. The user experience is way better because you go to the airport, you immediately can immerse yourself with all the shopping, all this stuff in the airport. You only do the security check finally before you board. Improve your user experience dramatically. Of course, it's more costly for the airport if you think about it. So why most airport I know of choose the first option, which is multi-level of the security check. Well, the idea is if something goes wrong at one level, you don't have to go back and redo everything. You only need to backtrack one level. Does that make sense? For example, if something wrong after you realize, the agent of the airline realized something wrong after I have boarded all the people to my plane. All I need to do is deplane everybody and ask them to rescan their boarding pass to enter the plane using the current approach. If they're using the alternative approach I have proposed, what they have to do? You have to deplane everybody, ask everybody grab their stuff, go outside, take out shoes and scan everything again. Does it make sense? I hope it does make sense to you what I'm saying, right? So it's very expensive if something goes wrong. That's why they implement these multiple levels of check and using a modular approach. That's kind of the reason why, right? So log, that's why we call this checkpoint. Same thing here. Intuitively speaking, the reason we enforce the checkpoint is to avoid, in case something goes wrong, we don't have to go back all the way to the beginning of the log and redo everything or undo everything. We only need to redo and undo back to some point, back to the last checkpoint. Pretty much like what happens in an airport security check scenario. Does that make sense to you? Okay. Of course, that's the high-level idea. It's always the details that matter. Right? High-level idea are always easy. A car has 4 wheels. That doesn't mean I can build a car. Everybody knows about that. What differentiates you from the others is you know the details. Okay? So now let's dive into the details of how this is actually done. Okay? In order to understand what's going on, unfortunately, I have to introduce additional things. With the stuff we have so far, we're not able to solve this problem. So I will introduce two more guys. One is called transaction table, the other is called dirty page table. Transaction table has one entry per currently active transaction. An active transaction is any transaction that has not done an AMP log record yet. Even if you have declared commit or abort, you are still considered an active transaction. However, there's a slight difference. Before commit, a transaction is called running. During commit, a transaction is referred to as committing. During abort, a transaction is referred to as aborting. So they are all active transactions, but there are slightly different type of active transactions. So you have one entry per active transaction in the transaction table, which has three fields: transaction ID, status, and last Alison. The status can be either running, committing, aborting. The last Alison document what's the latest log sequence number produced by that transaction, which is updated through the course of running this transaction, of course. Now, whenever a transaction declares AND, meaning I print out an AND log record, you remove that entry from the transaction table. Is that clear? So fairly straightforward, the transaction table. The next thing is called dirty page table. Dirty page table, DPT, documents every single dirty page currently in the buffer group. In other words, it has one entry per dirty page currently in the buffer group. It contains one field called record Alison, and also, of course, the page ID. That's how you document which page is dirty currently in the buffer group. So page ID and REC Alison. REC Alison, here is the critical part, documents the first log record ever caused the page to be dirty. This is to be compared with page Alison. Do you remember what page Alison is? You just said that, right? Page Alison is the last log record causes the page to be dirty, and which is associated with the page itself. So page Alison is on page. It's on the page. REC Alison is not on the page, but associated with the page ID on dirty page table. One document, the first one causing this page to be dirty, of course, I have to define that, right? Otherwise, it's like goes all the way back to history, right? The first log record caused this page to be dirty since last committed version of this page. So whenever you commit a page, REC Alison will be reset. Page Alison is the last log record causing the page to be dirty that's not committed yet. So that's the difference of the two. Okay? You may wonder why we need to know REC Alison. Well, the idea is, in the case of failure, system failure, how far you need to go back to perform redo in the worst case to make sure durability is guaranteed. Well, you only need to go as far back as REC Alison. You don't need to go beyond that, because going beyond that, those are committed version of the page on disk. You have committed version of those pages on disk, so you have to go beyond that. That's why we need to know REC Alison. Does that make sense? Okay. So, here are all the players. We have the logs on disk and in memory as well. There's the slack between the set of log record on memory and the set of log record on disk. The difference, the slack, is indicated by flash Alison versus the latest Alison on memory, right? And we have the database, we have data pages, each has a page Alison. You have committed version of pages on disk and uncommitted version of the pages in the memory. And every page has a page Alison. For everybody on disk, page Alison is less than or equal to flash Alison. For everybody on memory, page Alison could be either less than or greater than flash Alison, depending on whether the page has been flushed to disk or not. But the requirement is, whenever you try to flush a dirty page to disk, you need to ensure page Alison is less than or equal to flash Alison. So everybody on disk must have page Alison less than or equal to flash Alison because of that policy. Then there's something called master record. Master record is the Alison log sequence number document the last the last checkpoint you have ever performed. That's what we call master record. And this is essentially tell you where to go, where to start when the system fails. You go back to the last checkpoint. You don't go beyond that. In main memory, in the RAM, you have three things. You have the transaction table, dirty page table, and flash Alison. Those are the players in main memory. Okay? So normal execution of transaction, it's each transaction is a set of read and write, followed by commit and abort. We assume that this write is atomic. What does it mean? Meaning that when you grab a page, either it's a data page or page of log records. By the way, log records are organized by page as well. You don't write a single log record. You don't read a single log record. You always write or read a page of log records. Okay? You treat log record just as a database record, essentially. And they are organized into database pages as well. Okay? I hope at least one thing you learn after taking this class is you never ever write a single object to disk. You always do buffer read, buffer write. At least you should do that after taking this class. Okay? If you don't do that, I feel honestly miserable of teaching this class. I feel like I've been all my efforts are in vain teaching this class, right? So that the reason I mentioned this is I need to explain what an atomic write is. Because you are writing a page of data to disk. A page of data is 4K or 8 kilobytes, or even 16 kilobytes, depending on your system configuration. This takes time. What happens if system fails, if you are so unlucky, in the middle of writing a page? 4 kilobytes, if each sector is 512 bytes, that's 8 sectors. Suppose they have finished writing 4 sectors, and there are 4 more sectors that are not written to disk yet, and system crash. What do you do? Well, database has special mechanism to ensure to recover from that. I'm not going to talk about that because that requires database system work hand in hand with something called block device driver. You know what block device driver is? Block device driver is the driver program that controls the hard drive. Okay, fairly low detail stuff, low level stuff. I'm not going to dive into that low level of system issues. So for us, we simplify this a little bit. You assume that each page write and read is atomic, meaning either the entire page is written to disk or nothing was written to disk, like mini transaction. Think about it like that. That make sense? In fact, block device driver use something very similar to the concept of transaction to ensure each page is atomic. You basically view the sequence of the sector write, enclose that as a mini transaction. You do block device driver, inside block device driver, you have something like cache, and you use something very similar to the concept of transaction to ensure atomic write and read of pages on these pages. And we're using straight-to-place locking, meaning what? Straight-to-place locking means that you don't have to worry about cascading abort, and you are dealing with only serializable schedules. Okay? And finally, we're using still a no-force buffer management plus write-ahead locking. Okay. So normal transaction commit in an ideal world, when everybody obeys the law, everybody follows the norm of human society, a lot of issues are gone. If that's the case, if everybody follow the law and everybody follow the norm of human nature, I can cut on U.S. government budget by a lot. All police, you're out of job. U.S. military gone. You don't need that anymore, right? So let's talk about the ideal case. Let's talk about the ideal case. The ideal case is you write the commit log record. Okay, so the log type is commit. And all log record up to transaction commit record are now need to be flushed to disk. In real system, it's not necessarily the case that you flush all of this at once when transaction committing. Some of them may have been flushed to disk already, but some of them may not have been flushed to disk yet. So the remaining ones, you force them to flush. This guaranteed flush Alison is greater than or equal to the last Alison, which essentially translates to the second requirement of write-ahead logging, which is a transaction can only commit if all the log records of the transaction have been forced to disk already. So that guarantees the second condition. Log flush are sequential synchronous writes to disk. So what is synchronous write, by the way? You guys probably heard of synchronous write, synchronous read, asynchronous write, asynchronous read, write all the time. Can someone explain to me what does it mean? Synchronous write.
Writes at the same time.
Say again?
Writes at the same time.
No, I mean, literally that's what it means. But if you think about it in a physical world, that's impossible, right? It takes time to write. What do you mean by write at the same time? Yeah.
So if it's synchronous, that means that, so like you start one like log flush, and then your code like pauses and waits until that's done, and then it goes on to the next one.
Somewhat, yeah. So synchronous write basically means, you can think about this as a distributed system. You have two parties. One is memory, one is disk, okay? Synchronous write means that you always wait. A write is only considered completed when you receive an acknowledgement from the other party. Asynchronous write, like, I just issue the write command. I don't really care actually that the write has happened or not. I proceed with my subsequent write. Which means either the write can fail or sequential write from the eye of memory now may appear out of order on disk. Well, the first write, yes, you issue the first write, but it actually happened after the second write. They may arrive out of order. Does that make sense? Synchronous write ensure that every write actually happened and all the writes are in correct orders. Of course, they introduce overhead because you have to wait for the other party to acknowledge. Okay, that's synchronous write. You can generalize this concept to any distributed setup, right? Involve one or multiple parties. Synchronous write, synchronous read basically is what I said. Asynchronous write, asynchronous read is the opposite of what I have just said. Does that make sense? Okay. Now, once you do all of this, commit returns. By this point, I ensure that, and I write record to the log, and I also delete the entry of the transaction from the transaction table. Okay? So this is normal transaction commit. What about simple transaction abort? Simple transaction abort, basically you want to undo the changes made by the transaction because of the atomicity requirement. Like, this transaction has never happened before. You erase this guy altogether, essentially. So you get the last Alison of transaction from the transaction table. Remember, transaction table has transaction ID, status, and last Alison of the transaction. So you get that from the transaction table. And you write a abort log record before start rolling back operation of this transaction. So you follow the chain of log record backward using this previous Alison field I explained earlier. And you write a CLR compensation log record for each undo operation. So why you need to write CLR for undo? Why? Because undo is essentially another update you did to the database. And you are still using no force and steal while you are doing undo, which means the changes made by this undo, by this type of update, may be lost as well when system fails. In other words, you need to document undo, document all updates, so that later on you can redo these updates. In other words, you need to make sure you are able to redo the undo. You need to make sure you are able to redo the undo, because undo is an update. And that's why you need to introduce a log record for that, to compensate that. That's why it's called compensation log record. Okay? You need to redo the undo.
So I guess throughout all this, do we assume like once a log record is written, like assuming we're not like checkpointing and doing that sort of thing, we assume that once something is written, you don't ever change it to the log, or?
Yes, log record, no, you don't go back and update log record, of course. Okay, how do you undo? Well, given a log record, you can easily undo, right? Because you have the offset, you have the length, you have page ID, before image, after image. You take the before image, override the after image. That's the undo process. Okay, so very easy. So this explains the abort process. The key point is you continue logging while undo. Because undo are a sequence of updates, and you are using no force, and still during this sequence of updates, you want to make sure you log these activities so that you can redo these updates. In other words, redo the undo. Okay? So compensation log record has one actual field. It's called undo next Alison. This is really to facilitate a system crash during the abort process. You can come back and quickly figure out what's the next one to undo. That means that undo next Alison is nothing but the previous Alison of the current record you are trying to undo. That's essentially undo next Alison. Another key point is you redo the undo, right? That's the point you continue logging. You're using this CLR. But you never, this is somewhat confusing, but once I write it down, I hope you guys will understand, right? You never undo the undo, right? Now you can understand why I mentioned inception in last lecture. You never undo the undo, right? Does that make sense? No? If you undo the undo means that you have done nothing. Okay? In other words, greater than one undo won't happen. You undo once. But you may need to redo the undo multiple times if the system keeps crashing while you're undoing that. But you never undo the undo. So they might be way down when repeating history to guarantee at least there's one undo. The point of redo the undo is to guarantee at least there's one undo. Okay. This also implies for each undo action, that you have performed, it will produce at most one compensation log record. Because each compensation log record indicates an undo operation. You may need to redo that CLR multiple times, but you don't produce more than one CLR for each undo operation. Each CLR indicates exactly one undo. And you produce exactly one CLR for every action that you need to undo. You don't produce multiple CLR for the same undo action. Yes, you produce multiple CLRs for the same transaction, not because that transaction has multiple actions to be undone, but one per undo operation. Okay? At the end of all undos, you write an AND log record. You're done. Checkpoint. So the checkpoint process, I explained before, is to ensure that after you pass this gate, system knows that you have completed certain check. Just pretty much like you're going through an airport security check. After you go through the counter, system knows that you must have your boarding pass. After you go through the security checkpoint, I know for sure that you don't have guns, knives, all this stuff within what you carry on. Hopefully that's the case, right? You never know for sure. Hopefully that's the case. Okay? So what's checkpoint? Checkpoint, if we don't have checkpoint, what we will need to do is go back to the original history, the very first log record, that you started running your database, in case of system failure, that's where you need to go back to. Right? So the point of checkpoint is to document the status of the database at various points in history. If you allow me to go back to this image here, all players, these guys are on disk. Log record are, I'm talking about those, those ones being flushed to disk. Right? A lot of pages have been flushed to disk. A lot of log record have been flushed to disk. Yes, there are some dirty pages, and dirty pages for both the data pages and log record are cached in memory that were not written back to disk yet. That's okay, I understand that. The vast majority of these guys are on disk. Right? What are the two key pieces of information that's not permanent? A transaction table, dirty page table, and master record. These guys are vulnerable in the face of system failure. So a checkpoint takes care of that. A checkpoint, of course, there are multiple variants of what checkpoint does. Right? In commercial database systems, they use something called two-phase commit. I'm not going to talk about that. We talk about a simplified version of checkpointing process. So in the simplified version of checkpointing process, what you do is you take these guys, and what do? Write them back to this. You make them safe. Now, what you have accomplished while doing that, when system crash later on, you can go back to this point in history, the last checkpoint you did, restore the content of dirty page table and transaction table at the point of checkpoint, so that you can replay the log from that point onward to restore the system status rather than going back all the way to the beginning of the history to restore the status of system at the time of crash. That's the point. Of course, unfortunately, it's not as simple as I described. Otherwise, I can call it AND and I write an AND log record right up. But it's not. The tricky part is transaction table and dirty page table may be huge in a large database. You may have thousands and millions of transactions. Writing of these two tables to disk, unfortunately, cannot be considered as atomic. System may crash in the middle of writing these tables. Does that make sense? Checkpoint is not atomic. That's challenge number one. Henceforth, what you do is you write a begin checkpoint log record and write an end checkpoint log record. What you do is the following. At the begin checkpoint process, you make a copy of the two tables and put them aside and start writing the copy of the two tables to disk. The reason is because this is not atomic and because this takes a long time, one option is while writing the two tables to disk, you log them so that nobody can make changes to the two tables. But that obviously impacts the performance of your system. So what most systems do is continue logging, meaning continue transaction execution in the process of checkpointing. So you take a snapshot copy of the two tables at begin checkpoint. You write the snapshot of those two tables back to disk. While you are doing that, you allow updates to continue to happen to the two tables. At the end checkpoint, what that indicates is you have finished writing the images of the two tables at begin checkpoint. Okay? Not at the end checkpoint. Okay? So that's essentially what happens. And you also store, of course, log sequence number of the most recent checkpoint. In other words, the last end checkpoint, that's your master record. You write that back to disk. But the master record indicates you have a copy of the two tables at begin checkpoint, not at the end checkpoint, even though the master record itself is the end checkpoint. But it tells you you have the copy of two pages at the begin checkpoint time. not at the end timestamp, end checkpoint timestamp. Okay, that's another subtlety you guys need to understand. Now clear? All right. Okay. So far we've been describing the society that no police, no army, and no nothing like that. Okay. Now back to reality. Reality is bad things can happen. Unfortunately, bad things can happen, and you need to be prepared for that. That's why you pay tax. Okay. That's why you pay tax. Okay. So what do? What's your tax? What's the price you have to pay? The price to pay is all this log stuff we have done, and when bad things happen, when system crash, you have to redo and undo. You have to redo and undo. So the big picture for system crash is the following. You do an analysis phase. This is the point of crash. You look at the last checkpoint from your master record. You look up that. You do an analysis. The analysis phase, if you think about what analysis it does, in high level, is actually fairly straightforward. From the last checkpoint, you load the contents of those two tables, dirty page table and what? Transaction table from disk. But the content of these two tables reflects the state of those two tables at this point, not at this point. Does that make sense? So what do? While you play the log, you replay the log from here to here. What's here? This is your flush, Alison, the last log sequence number you flush to disk. And you replay this log like you replay the history and restore the contents of these two tables to the point right before the crash. Does that make sense? Okay? But there is a catch. There are actually two catches. Let me explain the either one first. The first one is because of this. Yes, luckily I still have this. And have not erased them yet. I've not flushed them yet. Because of this, you on disk, you only have log record up to flush Alison. But at system crash stage, you may have a few more log records in memory that are not flushed to disk yet. At the point of crash, what happens? These guys are lost forever. Does that make sense? The impact of these guys to dirty page table and transaction table as a result of that, there's no way to recover them. Unfortunately, there's no way to recover them. So, in the best case, at the end of the analysis phase, you actually recover the content of dirty page table and the transaction table up to this point, but not up to here. That's observation number one. Is that clear? Okay? Observation number one. Observation number two. The second one is even more important and a little bit even more trickier to understand. Observation number two is that the dirty page table, if you think about it, the dirty page table, documents all the dirty pages currently reside in your buffer. Because we never log the activity of buffer, we don't know who replaced what dirty pages being written back to disk. We never document that, right? We never document buffer manager's activities. We don't really know before crash. Suppose this is last checkpoint. From here to here, we have the content of the two tables right here. And we start replaying the log to reconstruct these two tables. But because we don't know the buffer manager's activities in between, we actually don't know who has been removed from the dirty page table. In other words, if buffer manager had written a dirty page to disk in that period of time, that page would have been removed from the dirty page table. But we don't know that. Because that image of dirty page table is lost during the process of crash. And we don't document activity of the buffer manager. You may wonder, oh, what a miserable work. What do we do now? What do we do? Well, I'll give you a simple analogy. Somebody tell you, go to Las Vegas, you need to carry $500. In order to survive on the, $500 is the maximum you can lose, so that they don't detain you, the casino don't detain you, right, for owing their money. And you will be in trouble carrying $400. But if they tell you, you need $500, right? Oh, I carry $20,000. Is that good enough? For sure, have a good time in Las Vegas. The idea is, the reason I mention this is, we are still okay, because if you think about it, our dirty page table, our reconstructed dirty page table, actually is a superset of the actual dirty page table right before crash. Because we have everything you have, and we have those you have removed from my dirty page table. So I'm actually a superset of what you have. And your goal is to redo and undo. If I have a superset of what you have, I'm obviously okay. Yes, I will do some unnecessary work because of this. Because in my view, page A is still dirty. In reality, it's no longer dirty. This version is already committed. I don't know that, but that's fine. I just double check and make sure it's okay. I have a superset of that. So that's kind of the idea of it. Yes? You may wonder, then what about these guys? What about these guys? You are not able to reconstruct the effect of this to dirty page table and transaction table, right? What do you do? Well, the good news is because of red hat logging, what's the requirement? Any change caused by those folks to data pages must have not been committed to this yet. Because the requirement page Alison must less than or equal to flush Alison. So I don't have to worry about these guys. Those changes are gone. Like phantom, never exist. So I cannot reconstruct the impact of them to my dirty page table and transaction table, and I don't have to. You are phantoms, like never exist before, because of red hat logic. So we're good on both ends. Even though we're not able to reconstruct the exact image of dirty page table and transaction table, magically we're still okay. Okay? All right. Now you have reconstructed this dirty page table and transaction table, not exactly the image of the two right before crash, but it's okay. As I explained. Once you have done that, what do? You first do the redo, make sure durability is honored. How do you do redo? Well, that's where dirty page table comes in handy. For all the pages in the dirty page table, you potentially need to redo them. How far you need to go back? You need to go back to the very first REC Alison, the smallest REC Alison back in history, and perform redo from that point onwards. That's where you need to start redo. What about undo? Well, for all active transactions in transaction table, you need to undo. Because those are the transactions who haven't committed yet. In order to ensure atomicity, you need to make sure they are like never happened. So you need to undo everything, all the transactions in the restored transaction table. And you undo, how far you need to go back, that I don't know, depending on how far the first record appeared back in history for the every active transaction in the transaction table. You basically follow the chain to undo. While you are doing the undo, what do? For each undo, you write a CLR. Unless a CLR already exists for an undo operation. What does it indicate? That indicates you must have been here before. You must have undone this in the past. It's in the process of that undo, you crash again. It's like you are in a level of drain of drain. You break out the first level of dream, you come back, you realize, oh, I'm still in another level of dream, like in the movie of Inception. So when you see a CLR, what do? You skip that in the undo process, but you do need to redo that CLR in the redo phase. Yes?
So how do you know, so when you're in this undo phase, I'm just imagining like going through the log, how do you know, like without looking ahead into the log, whether some particular action already has a CLR with it or not?
CLR always appear after the original update log record. So undo going backwards. So you always encounter the CLR before you encounter the corresponding update log record.
So redo, you do that.
Redo, you go forward, undo, you go backwards.
Oh.
So you always encounter the CLR. Does that make sense?
Yeah.
Okay, cool. Very good question. Okay. Now let's look at this in some more details. Analysis recovery, you scan the log forward from checkpoint. Whenever you encounter an record, you remove the transaction from the transaction table. For all other log record, you add the transaction to the transaction table. If it doesn't exist there, yes. If it already exists, you update the last log sequence number to the current log sequence number you are looking at. And for each update record, if a page key is not in the DPT, dirty page table, you add a page to the dirty page table and set REC Alison to Alison. But if the corresponding page already exists in dirty page table, you do nothing. You do not update its REC Alison because REC Alison is supposed to document the smallest log record, causing the page to be dirty. So only the first one you encountered, you insert this to the dirty page table because you scan the log forward during the analysis phase. Okay, so that's the end of the analysis phase. Analysis actually is easy. And redo and undo. You redo, like I said, you reconstruct the dirty page table, you look and you find the smallest REC Alison for all dirty pages. And you start scanning log record forward from that point onwards. Okay? For each update log record or CLR, this is the point. You need to redo the undo. So for each update log record, obviously you need to redo. For each composition log record, it's an undo is the update, so you need to redo the undo as well. So for each for each update and CLR, you need to redo that operation. However, in the worst case, you redo all of them. But actually, you can improve the efficiency quite a bit. How do you improve the efficiency? First of all, if the corresponding page of that update log record or CLR is not in the dirty page table, what does it mean? What that means is this update of CLR log record indeed happened after the smallest REC Alison for some pages in your dirty page table. However, the corresponding page is no longer dirty. It was written back to disk before the last checkpoint. So you don't have to redo this update. You can, but you don't have to. It's already committed. That's case number one. Case number two, a affected page is not in dirty page table, but its REC Alison is in the dirty page table. But its corresponding REC Alison is greater than the current log sequence number. What that means is the following. What that means is the following. Suppose I have my dirty page table. Page ID, REC Alison. Suppose I have page ID A and REC Alison is 10. Now on my page, and I have another B, which is 5. So, which means the earliest one calling page B to be dirty is log sequence 5, whatever. And then I scan log record forward from here, that makes sense, for my redo phase. Now, at log record 8, I say an update to A and blah, blah, blah. But my dirty page table says the REC Alison of A is 10. What does it indicate? That indicates log record 8, this is supposed to be the update log record. This log record indeed has caused page 8 to be dirty in history. However, it was later, what? Written back to disk. It was committed to disk. So on disk, for the page A, the page Alison must be greater or equal than 8. Why I know that? Because otherwise the REC Alison cannot be 10. Because REC Alison is supposed to tell you the earliest log record causing this page to be dirty and not committed yet. The fact that your dirty page table tells you this is 10 means that, yes, there must be another update to A at 10, but in between of these two, buffer manager had written this back to disk and reset, remove this from disk. So at one point this was 8, but it was removed, and then subsequently another update, that's why it's become 10. That's the only possible case for record ISM to be 10, but not 8. That's why you don't need to redo this update. Okay? The last case is the trickiest of all, which takes some effort to understand. Which says, okay, the first two cases do not apply. So I find the page in the dirty page table. Let me show you that. Let me say, okay, I find this to be A, this is 10, and I don't have to, I can skip this, but I do need to take up this, take up that, right? Now, when you try to redo this, what you realize? You realize on disk, this has 15. So what you do is, you need to redo this by loading this page to buffer. But once you load this to buffer, you realize, okay, this is page A, my page Alison is 15. What does it tell you? You're at this point, you haven't seen log record 15 yet. But you know for sure, after seeing this page Alison equal to 15, even without looking at the log, you know log record 15 must be an update concerning page A. And the fact that page Alison equal to 15 means what? That log record must have been written back to disk. That also implies if the update by log record 15 had already been written back to disk, this update no longer matters. It was overwritten by a subsequent write. So you don't have to redo this. You may wonder, if that's the case, if page Alison for page A was 15, why not REC Alison is something, isn't that should be something greater than or equal to 15? Yes. In the real dirty page table right before a crash, that must be some value greater than or equal to 15. However, because what I explained earlier, because we didn't document what buffer manager does, we were reconstructing dirty page table purely based on log. We didn't document the fact that buffer manager took this page and read it back to disk. We don't know that. Henceforth, our reconstructed record ISN is always going to be smaller than or equal to the actual record ISN for those pages on dirty page table. But that's okay because we ensure the safety of it, impact the efficiency of it a little bit. However, even in this case, we can still save efficiency a little bit. Yes, we paid an unnecessary rate, but at least we don't have to write it back to disk if we realize that's the case. Finally, the real redo, the only necessary redo you have to do is page Alison is 10. Sorry, page Alison was 8. Meaning that this was committed. This is guaranteed actually. Because if you REC Alison 10 means that this must have been written back to this even before checkpoint. And it happened that on this image, page Alison equal to 8. Now you're redo 10. Now you do need to redo and write this back. Of course, by the way, during redo, we are still using no force. What does it mean? You redo this page, you reapply this update for the buffer copy of this image, you don't force this back to this immediately. you are still using no force and still with red hat logging. You don't force this back to this immediately, meaning that this redo may be lost forever if system crash again in the face of redo. So you might need to redo the redo multiple times. But if you think about the good news is you don't have to log redo, because redo once is the same as redo million times. So you don't have to log redo. But you do need to log undo because you need to redo the undo. And you never need to undo the redo. You need to redo the undo, but you never undo the redo. That's why you don't log redo operations. Okay? So that's the redo phase. Undo, I think I will leave this for you to explore. This is essentially an identical process like the abort process. Abort process. Okay? So I think there's nothing really I need to talk about here. Okay, the only thing here is that actually for undo you have two choices. One is undo each transaction in sequence, meaning I undo the first transaction. For every transaction in the transaction table, I need to undo that. The two choices you have is undo one transaction, come back, undo the second transaction. Okay? That's obviously choice number one. But if you do that, what you end up doing is, suppose this is your log record, the log file. What you do is you end up doing this, come back, end up doing this, okay? So you do a lot of random jump back and forth. Second choice is better, which is, I know I have to undo all this transaction from the transaction table. And transaction table tell me the last log record of each transaction. So what I'm gonna do, I'm gonna push all this log record to a single set, ordered set. Ordered in descending order of their log sequence number, from the largest one to the smallest one. Then I undo them one by one. So instead of doing this, suppose I have two transactions to undo. One is indicated by this green log record. One is indicated by the black log record. So the first operation is to say undo this, undo this, undo this, and come back here and undo this, undo this. That's the first procedure I described. What really happened is I'm going to order them. So the last, initially my set is this one and this one. And I'm going to order them. So I will undo this first. Once I undo that, I load the previous Alison, write CR. That's my, to undo that Alison. So my set now becomes this guy and this guy. And this guy rank is still above this. So I keep doing that. So I end up doing this. So one backwards scan, I undo everything I need to do. So that's essentially the undo process. Okay, there are some examples. Okay, let me go through this example quickly. So suppose this is my log file. Begin check one, end check one, update, update. T1 abort, CLR. This CLR is caused by this normal abort. Okay? You're writing on CLR for log sequence number 10. That makes sense? That's a normal abort. Produce a CLR. T1 end, because that's the only one you need to undo. Update, update, crash. Now, what's the image of dirty page table or transaction table for this checkpoint? Can someone tell me that? What's the image of dirty page table or transaction table for this checkpoint process? This is the simplest of all I can think of, right?
So T1 will not be in the transaction table because it already had an end.
No. I'm asking the dirty page table and transaction table at the time of checkpoint. I'm not asking the content of these two at the time of crash.
T1 will be in there as well as T2. I don't think T3. Where does T3 start?
So at checkpoint, if you look at this log, at checkpoint nothing happened. Both of them are empty, guys. It's like at 4 a.m. in the morning, what's in Salt Lake City Airport? Nothing. Nothing. Nobody at checkpoint. Of course, unless you are, I don't know about you. The earliest flight in Salt Lake City Airport is probably 6 a.m. I don't get up that early to go to Salt Lake City Airport to pass through security. Okay, maybe 4 a.m. Some of you are really uptight, so you always arrive 2 hours before you fly. Okay, 2 a.m. Anybody at checkpoint in Salt Lake City? No. No. Okay? If you see somebody, tell him or her, go home. Come back again. So both of them are empty, okay, at checkpoint. Now, what are the content of these two tables? At the time of crash. At the time of crash, what are the content of the two tables? Let's look at transaction table. Transaction table has transaction ID, what? Last Alison, and status. What transactions are still active at the time of crash? Only T2 and T3. T1 has finished. Both of them are still running. The T2 last Alison is what? Is 60. For T3 it is what? 50. Right? Both of them status is running. What about dirty page table? Well, the answer to that is we don't know, because we don't know the activity of the buffer manager. But if we were to reconstruct this based on the log, what do we have? The first page called dirty is what? Page 5. T1 runs out. That makes sense? It's 10, log record 10. Note that the fact that the transaction has ended does not necessarily mean there are no dirty pages left behind by that transaction, because we're using no force. Even if a transaction has aborted, has ended, the page called dirty by that transaction may still be dirty. The only person determining who's not in the dirty page table, who's in the dirty page table, is buffer manager, nobody else. So potentially P5 is still there. P3 must be there. Most likely it still be there. Of course, people have been waiting back to this, we don't know, by buffer manager. And this update to P1 will cause P1 to be there as well. What about this update to P5 by T2? Will that update record Alison? No, because you document the smallest one. Unless it was written back to this by buffer manager before crash, and then if that's the case, then you will have P5 and 60. But during the analysis phase, you don't know that. There's no way you know that. You have no way knowing whether this was pushed back to this or not. To be safe, you have to leave this there as 10. So that's the reconstructed content of these two tables by the end of the analysis phase. Then from this, you perform the redo and undo. Okay? There are examples I will allow, I will leave that for you to study. Unfortunately, it takes way more time than I have, anticipated. So I will move around for another 2-3 minutes to talk about final. I won't be able to talk about those NoSQL, MapReduce, Spark. I will upload the slides to the course website. If you're interested, you can look at them yourself. I won't have time to talk about it. So for final, okay, here's the deal. What you need to do is review homework 3 and homework 4. That's all you need to do. And corresponding slides, of course. The final policy is the same as midterm policy, the same open book policy. There will be 3 problems in the final. I have finished the final setup already. There's 3 problems in the final. The first one is hashing and sorting. Test your understanding of linear extensible hashing and axial merge sort. For axial merge sort, pay attention to the things we talked about, like double buffering, sequential and random I/O. And what's the impact to the sorting cost if you do double buffering and or if you do block IOs. Okay, for linear and extendable hashing is very simple. The basic understanding of when do you split an overflow bucket and what's the result of that, and what's the impact to extendable and linear hashing respectively. Problem number 1, done. Problem number 2, query evaluation and optimization. You remember this running example I used to motivate the discussion of query evaluation and optimization? I start with the most basic version of joining the two tables. I start pushing down the selection. I change the join of algorithm and ask you to show the I/O of each case, right? You will have a problem just like that. That's it. But I won't ask you many cases. I only ask you 3 different cases. 2 base case and 1 case involving pushing down operators, selection and projection. And maybe writing the intermediate results to disk and load them back and all that. Another part of problem 2 is similar to what you did for your homework 3, which is to use sampling as a way to estimate statistical information about your table. In the homework, I asked you to use sampling to estimate the frequency of an item, right? In the final, I asked you to use sampling to estimate something related with frequency of item, but not exactly the frequency of item. But the proof of that, you need to show your estimator, and as well as to show that it is an unbiased estimator. The proof process of that is almost identical to the proof I show you in homework 3, but you need to understand that proof in homework 3. The key point is to use that indicator variable I talked about to show that it is an unbiased estimator. Problem 2 done. Problem 3, transaction. Transaction has 3 parts. One is, the first part asks you to check your understanding of concurrency control. You are given 2 schedules. For one schedule, I ask you to show what happened to that schedule using straight two-phase logging. You basically need to show a table with respect to time. T1 does this, T2 does this. Then you acquire log, maybe blocked, maybe you are allowed to proceed, you release it. That's it. For the second schedule, same setup, but now show this for non-straight two-phase logging. That's it. Which means you can release log early, but once you release log, you cannot acquire any new logs. Problem 2, this stuff I just talked about. But I ask you to only do the analysis phase. I don't ask you to do radio anomaly. You only need to understand the analysis phase. Basically, I ask you to show the content of the data page table and transaction table at the end of the analysis. You don't have to show the redo and undo after that. But the homework actually asks you to do the whole thing. Reconstruct the data page table, transaction table, as well as carry out the redo and undo. So the final test, a subset of your homework. Lastly, there's the multiple choice test on transaction. What's the impact of still no force policy, the combination of the 2 and all that, and locking. Ask you to make some multiple choice questions. That's it. That's your final. If you do your homework, if you do your study, I don't see how you can possibly fail the final. Meaning score something below 60. If you actually do review, if you actually spend some time reviewing the homework 3 and homework 4, I don't actually see how you can score anything below 80 points. If you actually seriously review homework 3 and homework 4, I don't see how actually you can score something below 90 points. So it really depends on how much effort you're willing to pay for this. But I don't see how you can score anything below 60. If you score anything below 60, that only tell me one thing: you don't care. You don't spend any time at all. You never come to lecture, you never review, you never do your homework. You just want to come to final, spend 90 minutes and get a good point out of it. That's impossible, I can tell you that. Okay, all right, I really had a good semester with all of you. I hope I wish you the best for the final test. Okay, all right, thank you.